In 36D, we have a radical halogenation reaction. So we have a peroxide and we have an HBr. The peroxide is going to be the radical initiator. That's going to be the weakest bond that's present. When we react this peroxide, it will split up into two pieces that are both OR radicals. These OR radicals can then react with something else. Let me draw those a little bit bigger. And the next most reactive bond that's present is this HBr bond. So we should expect to see this homolytically cleave. We'll have one set of those one of those electrons, rather, not a set, react with the one single electron from this radical, and we will produce ROH, just an alcohol. We will also have a bromine radical left behind because now that's the most stable radical that we have left. So now we have a Br radical and an alcohol. The Br radical is able to react with this double bond, adding its electron density into the double bond as a new bond. When we do that, we're going to take the electrons from the double bond to make that new bond, and we're going to leave behind the radical on the more stable position, so the more substituted position. So notice, because we actually add the Br as a radical instead of as something that's positive, we're going to have, or negative, we're going to have a different type of reactivity than we see with just plain HBr. In HBr, it's actually adding as a negative bromine. It's Br2, it's adding as a positive bromine. Here it's adding as a radical, and so we end up with the more substituted position be the one that hasn't reacted yet with bromine, and H be the thing that's left behind to react. So if HBr, this can go through a homolytic substitution and generate a new bromine radical while having this H end up on that position. So then we end up having the bromine on the less substituted position, the hydrogen, which we usually don't show, on the more substituted position.